so this is Lecture 3, Calc 3, Math 150, Multivariable Calculus. I am not going to look at the audience right now, I'm not going to look at you, but if I gave you a pop quiz today and asked you to define the law of cosines and to give the formula for a 2 by 2 determinant, you should hopefully be smiling and excited, yelling game on, or something like that. Okay? That's the level of how prepared you should be for today's lecture. You should be able to answer a basic question like that, because if you can, then that means we have more class time to talk about the more difficult, challenging concepts, to go into greater depth, to try to give more of a sense of understanding as to why things are true. So what I want to start off the class with is a problem from the first homework assignment, where I give you the parabola 16y squared, I'm sorry, 16y is x squared, so y is 1/16 x squared. Now here's the beautiful parabola. Here's the point 0, 0. And the problem says, consider the point 0, 5, and find the point on the parabola that's closest to this point. Now the argument that you had to look at for your homework showed that there is no point that's closest. That should bother you, that there is no closest point. Because when you look at this, it should be clear that there has to be some point that's closest. What happens to your distance from 0, 5 as you go higher and higher up the parabola? What happens to the distance? Yeah, it's going to get bigger and bigger and bigger, and it's going to go off to infinity. So I know if I just go up to a certain amount, from that point onward, clearly that's not going to be the closest point, because the distance from 0, 0 to 0, 5 is 5. So once I go sufficiently high, I know that can't be my closest point. Which are natural points to try which might be closest points? Can anybody give me any candidates? Feels like the class is on an uneven level today with how people are sitting. Yes?
The origin?
Yeah, the origin. 0, 0 is a natural candidate. Can anybody give me any other points that might be natural to try? Yeah.
Critical points.
Critical points of what?
The derivative.
Okay, so one is to write down the derivative. So the distance function, well, let's look at distance squared of xy is f of xy is going to be x minus 0 squared plus y minus 5 squared. And because we know x squared is 16y, we could actually get some function g of x is 16y plus y minus 5 squared. So that's a really good distance function to look at. And what you're saying is, well, let's calculate, oh, sorry, g of y. And you're saying, let's calculate its derivative, which is 16 plus 2 y minus 5. And if we set that equal to 0, we find the critical point. So what value of y makes this 0? I believe it's -3, because you would have 2 times -8 is -16. So you get y equals -3. Well, if you look at this, can y ever be negative? So there's no critical point. So there is no minimum. All right, we will see how well this works. I want you to tell me where you think I'm traveling the fastest. Okay? Oh, good. That time it actually tracked. It did not track in the first section. Much better. Where did I travel fastest? And I am so glad I'm not teaching 3 sections of this class. Yes. Yes.
When you hit the wall.
When I hit the wall. But that wasn't a critical point.
But it's
It's a boundary point. So the most common forgotten thing in calculus when you're doing maximization problems like this is to check the boundary points. What are the boundary points for this? Well, really, by symmetry, it's enough to just look on the right part. And so I could look at it as maybe x is greater than or equal to 0. Or if I want, I could look at it as y is greater than or equal to 0, if I'm looking at it as a function of y. So the boundary point is y equals 0. And so one of the reasons I like to do this problem is to just really drive home how important it is not to make any accidental assumptions. To remember that you have to check the boundary as well as the critical points. There are a couple of other natural candidates you could have looked at. You could have looked at whatever value of x corresponds to y equals 5. Maybe that's a nice candidate. Another candidate, maybe if this comes down and makes a perpendicular to the tangent, maybe that's a nice point to try. Turns out actually where its tangent is coming straight down to the bottom at 0, 0. If you can't solve a problem, maybe you can at least build some intuition by looking at some special cases. And so if I can't completely solve it, here's maybe a couple of candidate points, and I can show which is the best of these several candidates. It's not a full solution, but it's better than nothing. Okay, the next thing I want to talk a little bit about is proofs by induction. How many of you have not seen proofs by induction before? Okay, I need a volunteer for this. You have to have a legitimate, valid Williams ID.
Yes.
Okay. Yeah, I can't use this. It's missing. I'm sorry. I need a valid, because this could be, I need a valid Williams ID, can't be missing a corner. All right, thank you. Thank you. I'm sorry, but I mean, they could say that that's why things aren't working. Nice and rounded.
Okay, other cards too.
I'm sorry? All right. I'm going to prove that everybody is named Romulus. So you looked surprised, Romulus. Why are you surprised? So you immediately said, so you've acknowledged. You didn't say, but Professor Miller, my name isn't. So you agree that you are named. So you said, but your card is not valid. Your card is not valid. You knew that that was not the right name on it. We'll have to deal with this after class. This could be really bad with the registrar. So proofs by induction. And this is one of the best techniques we have. So you have some statement Pn, and you show P0 is true. Or maybe you start off with P1, depending on how you're doing the counting. And then, once we know that P0 is true, we then show that if Pn is true, then Pn plus 1 is true. And therefore, Pn is always true. So this is how proofs by induction work. So for example, let's go through this. We know by the base case that P0 is true. We've already shown that. Now, we are imagining we are in a world where we've shown if Pn is true, then Pn plus 1 is true. I can choose any value of n. What's a good value of n? I'm sorry?
2.
Not 2. I know P0 is true.
1.
So if I do 1, then I get, if P1 is true, then I would know P2 is true. What's a good value of n to take? 0. So if I take n equals 0, I know if P0 is true, that implies P1 is true. But I know P0 is true. What can I conclude? So P0 is true. P0 being true implies P1 is true. Therefore, which P? So P0 is true. And if P0 is true, then P1 is true. Therefore, P1 is true. Now I go back up here. If Pn is true, then Pn plus 1 is true. What should I take for n now? I should take 1, and I should now get P1 true implies P2 is true. But I know P1 is true, so now what can I conclude? So P2 is true. And you just keep marching down like this. So this is induction. It's often described almost as just walking up a staircase. And so once we know the initial step is true, if we can show whenever Pn is true, then Pn plus 1 is true, then we're done. All right, so the most common example that people typically use for induction is Pn is 0 plus 1 plus n is n plus 1 over 2. So this is the most common one. I'm not going to do this because it's done so many times. One way to prove this is you can actually bypass induction and just write the numbers 0 through n backwards. And if you write them backwards, 0 plus n is n. 1 plus n minus 1 is n. All the way up down to n plus 0 is n. So I'll let you think about that. We're going to do a more interesting one. Now, you have the advantage that this is the second class. 0 squared plus 1 squared plus n squared is n plus 1, 2n plus 1 over 6. And if you are from section 1, please don't watch the video now. But in section 1, I was acting, gee, I wonder if this is correct or not. Given that this is now section 2, I'm not going to pretend. I know it's correct. What would you do, however, if you weren't sure if this was right? So I believe that this is true. What could I do? Test it. So how would I test it? What would be the simplest test?
Plug in values for n.
Yeah, what's the simplest value of n to 2?
0.
0. So this is the base case, P0. Does 0 squared equal 0 times 1 over 6? Yes. I could test it a little bit further. Does 0 squared plus 1 squared, does that equal 1 times 2 times 3 over 6? Yes. I could test it further. 0 squared plus 1 squared plus 2 squared, which is 5, does that equal 2 times 3 times 5 over 6? Yes. This is a boring class. We have guests. We don't want to bore them. You guys I don't care about. But, we don't want people to see that this is what's going on at Williams. Also, at some point, enough is enough. You've convinced me that it's probably right. Let's prove it now. Right? So at this point, I'm now pretty confident about my formula. I tested it 3 times. I don't need to test it 3 times, but I tested it 3 times. So now we're going to prove it by induction. A lot of inductive proofs essentially follow your nose and just do the algebra. And we're going to see a lot of algebra today. Algebra is probably the worst part of Calc 3 for people. So the way things work is we assume Pn is true. And now we want to prove Pn plus 1. So we know that 0 squared plus 1 squared plus n squared is n plus 1, 2n plus 1 over 6. We want to study Pn plus 1. So we have 0 squared plus 1 squared plus n squared plus n plus 1 squared. And if you look at this the right way, it should scream to you what to do next. We are assuming Pn is true, and I have this new expression here. Is there any part of that new expression that looks familiar? So we've got 0 squared plus 1 squared plus all the way up to n squared is n plus 1, 2n plus 1 over 6. And we've got 0 squared plus 1 squared plus dot 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 plus n squared plus n plus 1 squared. What part of that new line looks familiar? Yes?
The 0 squared plus 1 squared plus n squared.
Yeah! And what does that equal by inductive assumption?
The n times n plus 1.
Times 2n plus 1 over 6. And now I'm supposed to add n plus 1 squared. You know, one of the advantages of having taught this class longer than you've been alive is at this point I really know how to do the algebra. Right? I have n plus 1 squared. Oh, I have an n plus 1 over here. That's good. I can pull out the n plus 1. This has 6 as a denominator, so I'm going to write this as n plus 1, 6n plus 6 over 6. And now all I have to do is I pull out the n plus 1 over 6. I take n times 2n plus 1 and I add 6n plus 6. And I check and see, is this the same as n plus 1, n plus 2, 2n plus 3 over 6. That's what happens when I replace n with n plus 1. So if it's true, then this is supposed to equal my statement with n replaced by n plus 1. All I have to do now is I just do the algebra. It may not be pleasant, but it's at least not too bad. I'm just multiplying some polynomials. And so I strongly urge you to actually fill in the details and finish the proof here. So do the algebra. And you will see that it is equal. It turns out this is one of the most important sums you've never seen or probably haven't seen the way your calculus classes are taught. If you want to make me upset, what team should you be rooting for? Yankees. What I'm about to show you is on the order of rooting for the Yankees in terms of just how bad it would be for you to do this. In math, we don't give out praise lightly. If you are called the fundamental theorem in a subject, you should have earned it. The only one I disagree with is the fundamental theorem of linear algebra. I don't think it really deserves the title, but it's won it. Fundamental theorem of calculus, that you should know. And I will assume f is continuous, differentiable, and I'll assume f prime is continuous. We don't need all these assumptions. How many of you have seen a proof of the fundamental theorem of calculus? Okay. How many of you have not seen a proof of the fundamental theorem of calculus? Math is not true because somebody tells you, and I have a degree from Princeton or I teach at Williams. You have to be able to justify and prove it to someone. This is one of the most important results in all of mathematics. So we will see a proof of the fundamental theorem of calculus later in the semester. And the statement is if I give you some function here, and here's a, here's b, and the derivative of big F is little f, then the integral x goes from a to b of f of x dx is f of b minus f of a. And what word goes with the left-hand side? This is the, I'm sorry? Close, not perimeter.
Well, I don't know how to say it in English.
Ah,
Area.
the area.
Oh.
So perimeter is the length of the boundary. Area is the area under the curve. If you forget to say area, you make me upset. Okay, almost to the point where I'd rather have you wearing a Yankee hat and talking about all their rings. If you don't include the area, it's a definition. The content of the fundamental theorem of calculus is the area under the curve can be computed by subtracting two antiderivatives. Absolutely amazing result. If your grade depended on it right now, how many of you could prove the fundamental theorem of calculus? Okay. Fortunately, your grade does not depend on proving it right now. If you wanted to try to convince me that this was reasonable, what could you try to do to convince me? You don't have to prove it, but how would you convince me that it might be true? How could you test it? So what could you do to test it? So I'm claiming for any little f, this is true. How would you test it? What could you do?
You try to find some area.
Yeah, so,
or curve.
so choose an f. What's the simplest f you could think of? It's okay to be really a smart ass right now.
X.
No. Way too complicated for your function.
1.
1. And if you wanted to be a real smart ass, you would give me f of x equals 0. Okay, f of x equals 0 is too much of a smart ass. F of x equals 1, the function that's identically constant, that's not bad. So if I try f of x equals 1, the antiderivative is just x. Oh my god, this is what we're excited about. We have found the area of a rectangle. This is like killing an ant with an elephant gun. Right? Now, I think, Romulus, what was the example you gave me next?
Let's try this in the theorem.
What's the next simplest function to look at? F of x equals
X.
x. And if I chose that, then big f of x would be x squared over 2. What shape is this?
Horizon.
So f of x equals x. How excited are you about finding the area under a... Yeah, right. I can't even pretend to be excited about this. It's still a test. It's still evidence in favor of the fundamental theorem of calculus, but we're finding areas of rectangles and triangles. We don't need calculus for this. But now, if we try f of x is x squared, then the antiderivative is 1/3 x cubed. This is finding the area under a parabola. And while I believe the Greeks had some ways of doing this, this is at least now finally a non-trivial problem to be looking at. And when you see that the fundamental theorem of calculus works, I will let you do the calculation. Now we can begin to see maybe there's something to this. And if you think about that sum we saw earlier, 0 squared plus n squared is n plus 1, 2n plus 1 over 6. If you look at this, what is the main term? Well, the main term is going to be 2n cubed over 6, or the main term, it's 1/3 n cubed plus smaller. And that really looks like the 1/3 x cubed. That when we're adding 0 squared plus 1 squared plus 2 squared all the way up to plus n squared, we're really doing a Riemann sum. And if we want to prove what it is, if we want to do those upper and lower limits, these are these things you do once in life, and then you have the fundamental theorem of calculus, so you never have to do it again. This is how you would actually prove what a lot of these upper and lower sums converge to. And this would give you a real non-trivial test. But what did I say I was going to prove? So I was going to prove something about everybody in this class. Yes. Excellent, Romulus. So who gets the extra credit for this comment? Romulus, of course. Right? So, so I am going to prove everybody's named Romulus. So Pn is the statement in a group, in any group of n people, all have the same name. And because we know the name of one person in the world, who do we know? Whose name do we know? Romulus. So everybody must be named Romulus, because if we can prove this, everybody has the same name, and we know at least one name. So proof. Is P1 true? That if I have a group with just one person in it, does everybody in the group have the same name? Yes. Not a big deal. Now let's do the inductive step. So apologies, my drawing sucks. So we'll have some people doing some disco moves. Some people may be sad. Some people have long arms. One, 2, 3, 4, 5, and n plus 1. Now, we want to show, we get to assume Pn is true. We must show Pn plus 1 is true. So in any group of n people, by assumption, they all must have the same name. Can somebody give me a group of n people from these n plus 1 people? I need a group of n people.
7.
What's 7?
My favorite number.
But I'm saying, I have these n plus 1 people. You have to tell me which n people from these n plus 1 people I should choose. So somebody give me a group of n people from these n plus 1 people. There's 2 very natural sets of n people from these n plus 1 people. Somebody give me a natural set of n people. So if you had 100 people, give me a natural set of 99 people. Which people? If I'm choosing 99 from 100, that's the same as choosing one person to exclude. Who should I exclude from this list? Yes?
N plus 1.
Yeah, exclude the last person. So here is a natural set of n people. Give me another natural set of n people. So you excluded the last person. Give me another natural set of n people. Who should we exclude this time?
The first person?
Excellent, Romulus. So we exclude the first. I'm sorry, Romulus. I forgot to say that that was a good comment. So you're cleaning up today, Romulus. So notice we have 2 sets of n people, and by the inductive assumption, they all have the same name. Person 2 is in both groups. Person 3 is in both groups. All of these people are in both groups. Therefore, everybody has the same name. Everybody's named Romulus. Now, this is similar to the first problem we did today, which is the point that's closest on the parabola to the point 0,5, and we initially got that there was no point, and you should just realize this can't be right. Most of you have a history of being called things other than Romulus. I know not all of you have that history, but most of you probably have a history of being called other things. So you should be suspicious right now at being told that your name is Romulus. What's the problem? Where's the mistake? Yes?
An assumption.
What's my assumption?
If any group of n people all have the same name.
Well, but that's what I'm trying to prove it. I'm proving it by induction. And I showed the base case when n equals 1. I showed that's trivial. When I only have one person in a group, they all have the same name. And now for the inductive step, I get to assume Pn is true. I get to assume in any group of n people, they all have the same name. So the mistake is that I drew this in a very misleading way. If instead I took n equals 1, what would happen when I draw things? Well, if n equals 1, what's n plus 1 equal to? 2. And so now, in this case, there's no overlap. It's a broken staircase. And if you think about it, if you knew that in any group of 2 people, everybody has the same name, then what you can do is just take Romulus and put Romulus in groups with every person one at a time. And since in any group of 2 people they all have the same name, then Romulus would force everybody to be named Romulus. We don't have that. This drawing is assuming that n is large, like 2 or 3. If n equals 1, it breaks down. And again, I really want to do these 2 problems to highlight to you how important it is to be careful and not to make additional assumptions. I love a lot of Mark Twain's witticisms One of my favorites is a cat that jumps on a lit stove will not jump on a lit stove again, nor will it jump on a cold one. For each experience in life, only draw from it the lesson you should. Is it true that everybody in the class is not named Romulus? I'm seeing people shaking their heads. Is it true that everybody in this class is not named Romulus? Yes. Okay. If people are having trouble with their name, we'll talk. Just make sure you use a good email account so I know whom I should talk to. Have I proved that everybody in the world is not named Romulus? Have I proved that everybody is not named Romulus? No. All I've done is I've shown that this argument does not prove that everybody is named Romulus. That does not mean that everybody is not named Romulus. It's an important point. Okay. So, proofs by induction are wonderful. A lot of them are follow your nose in terms of doing the algebra. The big thing to always be aware of is how easy it is to accidentally assume something and not even be aware that you are assuming something. And that is the greatest danger. Okay, so I'm going to assume now, because nobody had made any comments about it, that everybody is fine with the basics of, what is the dot product, what is the cross product, what is the law of cosines, and we're not going to spend class time on that, so we're going to be able to use the time to do something else. Oh, it doesn't want to go past. So, talk a little bit about determinants. So if I give you a matrix A, B, C, D, its determinant is AB minus BC. If I give you a 3 by 3 matrix, A, B, C, D, E, F, G, H, I, what I'm going to show you is a trick that gives you the determinant in the 3 by 3 case. These tricks do not generalize. And what I'm going to do is talk a little bit about what the determinant means and give you a little bit of a justification for why it does what it does. In the lectures, I went through and gave you a proof that it is the area. I'm going to give you a more heuristic proof that this is what's going on. If I could wave a magic wand and have you all take a class, I would have you take linear algebra. Why is it unreasonable to assume that you take linear algebra for this class?
This class is a prerequisite.
Yes, this class is a prerequisite for linear algebra. So to require you to take linear algebra when this class is required to be taken before linear algebra is not reasonable. I am sure you've had unreasonable professors and employees in your life in the past. You will have them in the future. I will try not to be in that subset. What I will do instead is I will concentrate on general dimensions when I can, but every now and then we will do things only in 2 or 3 dimensions when it will just make the linear algebra nicer. But if you know more linear algebra, when you take linear algebra, hopefully in the future, then you can come back and revisit this and things will make sense. So the way it works, it's a nice mnemonic, it doesn't work in general, is if I just write the first 2 columns again, and I go through this, then if you multiply diagonally like this and add all of these, and then multiply diagonally like this and subtract all of them, that's the determinant. And so that just gives you a formula to calculate determinants of 2 by 2 and 3 by 3 matrices. Now the reason we care about determinants is they give areas. And this is going to give you the area of the parallelogram created by the vectors A, B, and C, D. For the 3 by 3 determinant, it's going to give you the volume of the parallel pipette with those 3 rows. I have no idea what you call it in 4 dimensions. Call it hyperparallel pipette or something like that, or hyperparallelogram. We'll concentrate on 2 by 2 and 3 by 3. You saw how crappy my stick figures were. I am not going to risk drawing 4-dimensional stuff on the board. Let's think about what's going on. So can someone give, so if I give you, here's AB, and here's, say, CD. Then this is the parallelogram created by the 2 of them. And you can write this as maybe T times AB plus S times CD, 0 less than equal to TS less than equal to 1. So I walk down some amount on AB, and then I walk in the direction of the vector CD. And that's going to give me a parallelogram. What's the easiest parallelogram to find the area of? Square. And you can generalize square a little bit and be kind to me and say, well, instead of doing a square, we could consider a rectangle. So if I give you a rectangle, here is a 0, here is 0D. It is not hard to calculate the area of this rectangle, right? What is the area of Romulus?
AD.
Okay, I was wondering if anybody else was going to answer that, but okay, yes. The area is just AD. And if you think about a determinant A, B, C, D, well, C is 0 and B is 0, so that's going to just be A times D minus 0 times 0. Okay, so that gives us at least a test. We want to consider a more interesting parallelogram now. And what I'm going to do is I'm going to just shift the top a little bit. And so here I'm going to keep it at A0, and I'm going to move it to CD. What is the area of this parallelogram? Sorry, base times height. And the height is the same height as this. The base is the same as this. They have the same area. I strongly urge you to try to prove this. One of the things you can do is you could, consider the giant rectangle, find the area of the triangles, you could cut things up. There's lots of ways you can do this. But do the calculation and see that the area is unchanged. I am not proving that the determinant gives the area. I did that in the lecture you're supposed to watch. It uses the law of cosines. What I'm trying to do is give you a geometric interpretation of what this determinant is doing. And if I just translate things like this, I haven't changed the area. And now when I look at my determinant, it's going to be A0CD. And when I look at that, it's going to be AD minus 0 times C, or it's still going to just be AD. If I go to higher dimensions, if I go to 3 dimensions, it's going to be a volume. What is the volume of this beautiful piece of paper, this flat plane in 3-dimensional space? What is the volume?
0.
0. What's the volume of this? 0. This. 0. This is a 2-dimensional object in a 3-dimensional space. It has 0 volume. If I give you a line on a plane, what's the area of a line on a plane? 0. If I give you a circle, what's the area of the perimeter of the circle, the boundary of the circle on a plane? Still 0. All right. Now the next thing is, building on all of this wonderful stuff, we can look at the cross product. And so it's important to know, are you talking about vectors? Are you talking about numbers? What's your input? What's your output? For the law of cosines, if we have P and Q, I like to put arrows on them to remind myself that it's a vector. So this is the law of cosines. And I can say P dotted with Q is the length of P times the length of Q times the cosine of the angle between P and Q. Now what's nice about this is the cosine of theta and the cosine of minus theta are the same. So it doesn't matter which order I have the 2 vectors. Which is good because this dot product is just P1, Q1 plus Pn, Qn. It's not going to matter the order in which I put P and Q. The sum on the left is unchanged. It's good that the sum on the right is unchanged. Sometimes people don't like to use double absolute values. They sometimes overload notation, and they'll just write the absolute value of P. And they'll use that to represent its length. It's perfectly fine notation to overload things like this. I like to put The double lines, I like to put the arrows so that I can quickly look at it and remind myself, this is a vector, this is the length of a vector. When I'm doing integration, I wrote x goes from A to B. I don't really need to do that in one dimension when there's only one variable in play. Of course, I'm integrating over x. But when you have several variables, it's nice to have that so you can quickly glance down and see what's going on. This is the dot product. The cross product is a little bit more involved. All right, is everybody okay with the dot product? All right, so for the cross product, we have I hat, j hat, and k hat. So these are the unit vectors in the x, y, and z direction. I do not love this notation. If you are only living in three-dimensional space, it's fine. If you're going to go into four-dimensional space, what would you have after k? L hat. And if you have too many dimensions, you start losing letters of the alphabet and you're in trouble. If you're a Dr. Seuss fan, he does have a book, I think it's called On Beyond Z or something like that, where he adds letters to the alphabet. But even with Dr. Seuss, we can only go so far. I much prefer to use E1, E2, E3, because if I have to do 2020 dimensional space, I just go to E2020, not a big deal. But when you're looking at just 3 dimensions, a lot of books just use IJK. So then put my vector P, P1, P2, P3. Sometimes they do Px, Py, Pz. Doesn't matter which way you want to write it. Down here I'll do Q1, actually we'll use lowercase, Q1, Q2, Q3. And the determinant of this is the dot product, is the cross product. Now this is really an abusive notation to be writing this, because when you take the determinant, you're supposed to be putting in numbers, and I've got unit vectors over here. We're not going to let that bother us. I'm going to just use this to write down the formula. So I write down I hat P1, Q1, J hat P2, Q2, and I go through and I have my 3 positives, and I go through and I have my 3 negatives. And so when I go through things, I get that this equals I hat, and I'm going to have P2, Q3, and I'm going to leave some space because I know what's coming later. The next one is I'm going to have J hat times P3, Q1. And then the last one is going to be K hat times P1, Q2. Now we look at the minuses. The first one is Q1, P2, K hat. So that's going to be P2, Q1, K down here. I'm always writing my P's before my Q's. The next one for here is going to be P3, Q2 with an I. And then the last one will be P1, Q3 with a J. And if you look, it goes P cube, PQ, 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 2, 3, 3, 2, 3, 1, 1, 3, 1, 2, 2, 1. The order switches. And it goes 2, 3, 3, 1, 1, 2. Goes cyclic order starting with 2. If you look at this, P1, Q2 minus P2, Q1, that's a determinant. That's the determinant of this little part over here. If I just made P3 and Q3 be 0, this would actually be giving me the area of the parallelogram from those 2 directions. So this is the definition of the cross product. You can define anything you want in mathematics. Most of the things you choose to define are stupid and not worth defining. This turns out to be really good. Now, if you live in 3-dimensional space, if I give you 2 directions, how many choices is there for a direction that's perpendicular to both of them? 2. You can either go up or go down. So you're forced to lie along a line. If I live in 5 dimensions and I give you 2 vectors, and I say I want to be perpendicular to those 2 vectors, well, now I actually have a 3-dimensional space. This is one thing that's really nice. It's a trick that we have in 3-dimensional space, that the cross product will give us something that's perpendicular to both. Now what you can do is you can compute P dotted with P cross Q and Q dotted with P cross Q. Neither calculation is fun, but neither calculation is hard. You know, P cross Q, that's this vector. If I dot it with P, I multiply this one by P1, I multiply this by P2, I multiply this by 3, 3, and I add it all together. And when the dust settles and you do the algebra, both of these are 0. So this is just algebra that you need to do. Is it 0 the vector or 0 the number?
The number.
The number. P cross Q is a vector, and vector dot vector is number. So you really want to be able to just quickly look at something and say, what kind of quantity is it? And then, who is a lefty in this class? Interesting. We don't care about lefties. It is an acceptable category to discriminate against. Now, I have lefties in my family. My son is half lefty. Why? Well, we need to choose a orientation. We need to choose a convention. And the convention we've chosen is when you do P cross Q, you take your hand and you have your fingers curl from P to Q with your thumb pointing in the direction of P cross Q. And so you always use your right hand for this. Could you use your left hand? Yes, but then you'd be pointing in the opposite direction. Who are my econ or potential econ students? What's the horizontal axis? Quantity. What's the vertical axis? Price. So I drew a classic supply and demand curve. That's about the level of my artwork. Could you have quantity on the y-axis and price on the x-axis? Of course. What would happen to anybody looking at your paper? They go, wow, this is some funky demand curve. You want to use the same notation as everyone else so that when people quickly look at it, or when people are trying to process it, they can understand. You can use whatever notation you want, but unless you're a big shot, people are not going to adjust to your notation. Use the notation everyone else's. Later in the semester, sadly, we will have a little bit of trouble. I will try not to screw it up, but physicists and mathematicians have different notation for spherical coordinates. And I learned it from the physicists first, and my instinct is to use the physicist's notation. So I will try to avoid that. So P dot P cross, you could just do these calculations. And there could be some exam questions where I ask you to do something similar to this. More generally, if I give you A dot B cross C, this is going to be the volume of the parallel pipe head with rows A, B, and C. There's a nice geometric interpretation, and in fact, this is going to be the determinant A, B, C. Right. So there's a lot of stuff we did today. This is a really good day to judge how well did you do watching the video, and was there more stuff you wanted me to do in class that I did not? Right now, we're in the place where it's a lot of definitions, it's a lot of proving things, and do we really care about the proofs? This is a math department, so we care a little bit. That's why the video has a proof of the law of cosines. I am not going to make you prove anything at that level, on an exam, but you should be aware that these things can be proved. And you can see the interplay of the geometry. But this allows us to use the class time to talk a little bit more about connections, to review a little bit and connect back to Calc 1 and Calc 2, to do some examples, to really highlight how easy it is to make an unwarranted assumption. All right, so this is a good place to, we have another 20 seconds. All right, so you can start asking what other identities can you prove? If I flip P and Q, for instance, I would flip the two rows over here, and what you can see is, oh, that's going to just change everything by -1. That's going to change the direction. So unlike the dot product where order doesn't matter, for the cross product, order matters, but only weakly. All it's going to do is just change the sign. Rather than pointing up, it's going to point down. All right, so this is a good place to stop. And like the last one,